When we apply the energy balance specifically for an adiabatic CSTR reactor, it is important to remember that the inlet suddenly jumps to the outlet state when it is added to our stirred tank reactor. And that is not only in terms of the concentration, so the concentration of the outlet stream matches the concentration inside your vessel, but that is also true for the temperature. The temperature at which I must evaluate my rate inside that reactor corresponds to the outlet temperature of my CSTR. So if I do an energy balance over my CSTR in order to solve for that outlet temperature, that is the temperature that I must substitute in my mole balance when I calculate the rate. So the temperature where I need my heat of reaction and the temperature to which I must heat my inlet product, that is the same temperature which is the one at the outlet. So I consider a specific example on this slide for application. This, of course, is my epsilon value. The stoichiometric coefficient of component A there is -2. So this is del FA divided by the -2. Del H reaction is the same as at 298 because we assume that del CP reaction is equal to 0 for this scenario. So in this equation, I should note that I have two unknowns. The composition at the outlet, which I can write in terms of X, as well as my temperature. So I need another equation to solve for those two variables. And of course, the other equation is just simply my mole balance for component A. And I can write my rate is an additional unknown in that equation, but I have an extra algebraic equation to solve for the rate in terms of my unknowns, FA, and the temperature. What it boils down to is that for a single reaction, I can simplify my variables to be written in terms of just the conversion of A and the temperature out of and inside my reactor. And I have two equations. The first one is my energy balance and the second one is my mole balance. So what we are first going to do is to graphically represent what's happening when we solve these two equations simultaneously. As on the previous slide, I can manipulate my energy balance so that I make either temperature or X the subject of the equation. Of course, it's the easiest to solve that one. When you start with your own analysis, start with your energy balance, just make temperature the subject of the equation. For X values, that varies between 0 and 1. And in our previous video, we discussed the variables that will influence the shape of this line, the slope, and whether it's going to be positive or negative, whether it's an exo or an endothermic reaction. The mole balance, which is our second equation over here, is always a very non-linear equation where X is related to temperature, and mainly because of this Arrhenius temperature dependence. Of course, the other concentration dependence on the rate may also contribute to the nonlinear behavior of that equation. So what is shown on this figure over here is a graphical representation of where the mole balance is constructed simultaneously with the energy balance. So let's now just assume that it is an exothermic exothermic reaction, so we can neglect that line over there. And how this was constructed is you choose a range of X values, and I know my X must vary between 0 and 1. That's why it's a very convenient variable to choose. And then for each X value, everything is known except the temperature there in my rate equation. So I can solve the temperature for a range of X values, and then I can construct my figure. And of course, there where my mole balance and my energy balance intersects, that's the solution of the two variables by solving the two equations simultaneously. So in this specific reactor that I've just shown here, I can go for that. That is where my reactor will operate. This will be the conversion over the reactor, and this will be the temperature at the outlet, but also inside the reactor because it is a CSTR vessel. So the shape of this mole balance, does it look like that, or is it more curvy, or does it look like that even? Depends on several variables: the volume of my reactor, the volumetric flow rate, as well as the activation energy and my pre-exponential constant. So that is a seriously convoluted shape to try to figure out. It's not as easy to intuitively see what will happen to the shape of my mole balance like I could with my energy balance in our previous lecture video. So I can now graphically determine the solution for my conversion temperature relationship in a specific CSTR reactor, or I can use fsolve to get an exact answer. The graphical solution, what is cool about that is it gives me a very good idea of the first guess for my xt variable set that I would like to solve in my solver. Solving exothermic CSTR reactors, specifically exothermic, comes with a serious warning. Because of the shape of the mole and the energy balance, you can get a situation where the mole balance intersects the energy balance at several xt combination points. So several solutions are possible, and we are used to that for nonlinear equations. So what we must note is if I now use fsolve, I give it an initial guess. So if I guess initially my x is 0.5 and I guess a temperature, because I know it's exothermic, I guess a temperature that's just higher than my inlet temperature, it will definitely converge to that point. If I guess higher values, it can converge to that point. If I guess a lower value, so depending on the solution procedure it uses, it can find each of these operating points. So what is important to note is that this is not just a glitch, a mathematical glitch, and that, one is going to be the operating point where you will definitely operate. It does happen that you get systems for which the mole and the energy balance looks like the depicted in this figure, where it can actually operate at multiple steady states. And that can depend on where do you start up. So startup of that CSTR will then be very important. Do you approach it from a colder temperature? Do you approach it from a warmer temperature? That it can actually achieve either the high or the low steady state. This steady state in the middle is generally unstable. So what can actually happen in your reactor is you can happily be operating at the optimal high steady state, high conversion condition. There's a sudden drop in the flow rate. Suddenly there's a discontinuity, a drop, something happens in an upstream vessel. So just for a moment, the volumetric flow rate drops and then it comes back online again, and suddenly you find yourself operating over there. So your steady state, well, not that suddenly, after a while online, but suddenly you operate at a much lower conversion. And the explanation is that this is actually a steady operating state for that system. An even more precarious scenario can arise if there's a disturbance that causes the reaction to ignite. We call it moves past its ignition point. So instead of operating from, so this is the inlet temperature and it operates there at a mild temperature T and everything in your vessel is still nice in the liquid state, it can, due to a very small disturbance, because this is an unstable steady state, it can move to that higher temperature. And if you've got this exothermic reaction, this higher temperature that it suddenly moves to, so we've got this higher temperature suddenly, can be such that that temperature is higher than the saturation temperature of the fluid that you've got here in your steel vessel. And now I start to evaporate stuff, and it happens really fast. I start to evaporate, and what happens is that your tank, your reacting vessel, turns into kaboom, a big bomb. And there are instances where this happened in real life with disastrous consequences. You can read about it in your textbook as well as online examples where we've got this runaway exothermic reactions where multiple steady states was possible. So, word of warning is when you solve for CSTR reactors, exothermic CSTR reactors, please consider the graphical approach so that you don't just F-solve and say, yeah, I'm going to get a nice 90% conversion in this specific reactor. Evaluate whether other steady state possibilities do exist, and you can only do that by constructing, or not only this way, but the most convenient way of visualizing this is to construct the two equations that you must solve simultaneously on a single axis set. So how do we rid ourselves of this multiple steady state pickle? So let's say you inherited a reactor, so the volume is already fixed, that piece of steel, it's there. You must have a certain flow, you get something from an upstream vessel, so your volumetric flow rate, your inlet case and your stuff is fixed. So you cannot do anything about your mole balance. You can manipulate your energy balance by increasing your inlet temperature there to the reactor. So if I increase my inlet temperature, so when X is equal to 0, my inlet temperature will simply be, will simply be equal to that inlet temperature. That's that position over there. I shift my whole energy balance just to the right-hand side, and I move the equation so that it just intersects my mole balance once. Of course, increasing your T0 also costs money because you have to build a whole heat exchanger and you have to have a duty, a heating oil or steam that you can use to heat up your feed stream. If you want to manipulate variables in your mole balance, of course, this activation energy is something that is going to be out of your control because that is depending on the thermodynamics and the interactions between the different molecules. So that is not something that you will have control over. But you can size your reactor differently, and if possible, you can change your volumetric flow rate, except if that is a design variable that you will have no control over, but you can certainly change the size of your reactor in order to move your mole balance so that it only intersects the energy balance at your desired position. So therefore, always worthwhile to do these kinds of analyses before you start building stuff and ask somebody to check and help you check designs and think about the safety concerns with exothermic reactions in order to make sure that you practice or experiment with your design where the cost implication is not so significant. So just 2 slides that I would like to show you how to apply this, because we've done lots of algebraic manipulation in the slides to illustrate you the shape of the equations. So for instance, I have my inlet conditions. I've just chosen some inlet conditions. I've chosen the CP values and the volume of my reactor and a volumetric flow rate. So I have my parameters there. I checked my del CP of the reaction is equal to 0. So for a range of X values, picture you are doing this in Excel, and in fact if you want to, you can do it in Excel. Picture a range of X values and you know where it will start. It will start at 0 and it will go to 1. For each of the X values, you would like to calculate 2 temperatures. The temperature that will result in your energy balance and the temperature that will result in the mole balance. So for each of them, you want a value there. And of course, what you want to plot in the end is you want this on your y-axis and you want the 2 temperatures represented on your x-axis. So executing it in Python, this is what I want you to have in mind when you calculate it. And I want you to know what epsilon is. It seems as if it cut off there. So what's the equation for epsilon? It's del F of any component divided by its stoichiometric number. So I'm going to choose a range of X values and be warned that later in your mole balance, because of that rate equation, you may end up dividing the divide by 0 error if you start at 0 and you go to 1. So rather choose your limits to be not exactly going to starting at 0 and going to 1. So that's why my Lin space values look like that. Now I can calculate my molar flow rate out of my reactor. I can calculate my del FA and I know that my stoichiometric number for that specific reaction, there's the reaction that I illustrate here. I know that it is -2 for component A. I can calculate my epsilon, and now it's very easy algebraic manipulation to make this temperature the subject of your equation. So ask Python to help you simplify the arithmetic that you must do. I can calculate this sum of everything that was flowing in, multiply this energy carrying capacity over there, and there I've got my function that can calculate all my energy balance temperature values. Shown here, just to remind myself, this is the equation you want to solve. This is your rate expression for each of my x values. So this is just the parameters in my rate equation that was given. For each of my x values, I can calculate the concentration. I can calculate the rate from my mole balance. And from that rate, I can then use Arrhenius to calculate the temperature that will result for each of my different x values that will make this equation true. So now I have solved these equations and I can construct my figure. So you can inspect this now at your leisure. This is now where my operating point is going to be. But often your mean lecturer will require a more accurate answer than just reading it off the figure. So I would like you to be able to implement this in fsolve. So your solver will have two variables that it must solve. So you have to return two equations. The equations will be your mole balance and your energy balance. So I'm going to calculate xt is my variables. I can calculate an FA. I can calculate an epsilon for each x, the concentration, the rate for each xt combination. And then finally just my mole balance and my energy balance. So see over here, I already prepared for the occurrence that my del Cp reaction is not 0. I've calculated it previously, so this term will just fall away. So it's now going to try to solve it simultaneously, and I have to give it an initial guess value. So my guess value will then, I will require an x and a temperature, but look how well I can now guess. I am going to read off those values over there. And I can say like x looks as if it's going to be 0.9 and my temperature about, 650. 650. If you should go in guessing blind, at least consider whether you've got an exothermic reaction, then you know your temperature must increase, must be higher than your inlet temperature. And of course the conversion must be somewhere between 0 and 1.